let's take a look at fields and how they are described. So in situations where one object applies a force on another object from a distance, in other words, without the two objects touching, we say that the objects interact through something called a field. So for example, if we have a positive charge and a negative charge, even though they are not in contact, the positive charge is attracted to the negative charge, and the negative charge is attracted to the positive charge. We say, or we think about, this attraction occurring through something called a field. Also, if we have the Earth and the Moon. The Earth and the Moon, well, the Earth is attracted to the Moon is attracted to the Earth. They're not in contact. We say that this interaction occurs through something called a gravitational field. Now, the field at a location is quantified by something called field strength. So electric field strength is defined this way. Electric field strength is equal to F over Q, where F is the amount of electric force on an object, and Q is the amount of charge at that location. And then E gives us the electric field strength at that location. Gravitational field strength is defined this way. G is equal to F over M, where F is the gravitational force on a mass at a location, and M is the amount of mass at that location. Now, one little thing to notice here is that if we rearrange this, we get a familiar equation, F equals mg, where F is the gravitational force, M is a mass, and G, well, now we're calling that gravitational field strength, but in this equation that we've seen before, when we saw it before, we called that the acceleration due to gravity. The gravitational field strength and the acceleration due to gravity are the exact same thing. Near the surface of the Earth, that's equal to 9.8 meters per second squared downward. Just want to point that out. Okay. Now, if we want to display fields in a region, one very common way to do that is with field lines. Electric field lines follow some rules. They always point away from positive charges and into negative charges. They never cross. And the density of the field lines is proportional to the electric field strength at a location. So I can draw a couple situations here. We've seen electric field lines before, but just to remind you. Gravitational field lines always point into masses. They also never cross, and also the density of the field lines is proportional to the gravitational field strength at some location. So if we have the Earth and the Moon, we'd have gravitational field lines that look roughly like this. It's not a perfect drawing, but I did my best. Now, let's talk about potential energy. We've seen potential energy before, but in the context of fields, we can think about potential energy as the energy that an object contains. That's a little fuzzy, but it's the energy that an object contains or that's in a situation caused by the position of an object in a field. So I'm going to show you an example. Let's say here's the Earth. Here's the field lines, the gravitational field lines around the Earth. And then let's say we have two satellites, two identical satellites, one here and one here. The satellite that's closer to the Earth has less potential energy than the satellite that's farther away from the Earth. One way to think about this is if both of the satellites begin at rest and both just fall down to the Earth, the one that's further away from the Earth, when it reaches the surface, it's going to lose more potential energy in that travel, and it's going to gain more kinetic energy, right? It's going to be moving faster when it hits the Earth. So potential energy can be thought of as the energy that an object or a situation contains due to the position of something in a field. Now, we're going to define something called the potential. Now, the potential is different than potential energy. That's odd. They didn't name this because it's easy. But the potential is the potential energy per charge or the potential energy per mass, depending on whether we're talking about electric or gravitational field things here. So the electric potential is defined this way. The electric potential is equal to the potential energy per charge at a location. And the gravitational potential is defined this way. It's the potential energy per mass at a location. And using these two equations, we can get the units of both of these things. The electric potential would have units of, joules per coulomb. And the gravitational potential would have units of joules per kilogram. And if you look at both of them are scalar quantities. And the potential, it can be displayed or shown in a diagram using something called equipotential lines. Equipotential lines show surfaces which have the same potential across the entire surface. And we'll think a little bit more about that in a moment. But another fact about equipotential lines that's very useful is that they are always perpendicular to field lines. So for example, let's say we have an isolated positive charge. The field lines point directly away from a positive charge. The equipotential surfaces around that isolated positive charge would look like this. An equipotential surface is a surface across which you have the same value of the potential on that surface. Okay, and if we had a positive and a negative charge near each other, well, the field lines would look roughly like this, and the equipotential surfaces would look roughly like this. Notice that the equipotential surfaces at any location are always perpendicular to the field lines. So, equipotentials show where the potential is the same. And an object which stays on an equipotential, if it just travels along an equipotential, that means that it always has the same potential energy. Whereas an object, if it moves from one equipotential to another equipotential, it will change its potential energy, and so work has to be done. So, for example, let's say we have a negative charge. Here are the field lines, here are the equipotentials. If I have one object which travels on an equipotential and never leaves that equipotential surface, just travels along it, it never changes its potential energy, and no work is done. Whereas if I have another object which travels from this equipotential surface to this equipotential surface, well, if it moves between equipotential surfaces, then it changed its potential energy and some work had to be done. We can write expressions for the amount of work that's done in moving between equipotentials. For the electric situations, work is equal to Q times delta V, where Q is the amount of charge that you're moving, and delta V is the change in the electric potential. And W is equal to M times delta Vg, where W is the work that's done, M is the amount of mass that you move, and delta Vg is the change in the gravitational potential. Now, another thing about the potential is it will always, always, always equal 0 at infinity. It's defined that way, so that the potential always equals 0 at infinity. And the reasoning behind that is if you're really, 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 really far away from all other things, in other words, if you're at infinity, then you shouldn't be affected by that thing. And so we define the potential to be 0 when an object reaches infinity. Also, the potential increases to a positive value near positive charges, and it decreases to a negative value near negative charges and near masses. Now, both fields and potential are pretty abstract ideas. So if you're having trouble getting your mind around what they really mean, that's normal. They're pretty strange concepts when you first encounter them, and they become more normal the more you deal with them.